previous video, we looked at adjusting the growth model parameters based on using feed tables and formulas for FCR. In this video, we look at 3 other factors affecting final production. However, before going into detail on these, you should take a look at the 4 sheets labelled Growth Model 1 to Growth Model 4. These are the sheets where the daily feed input and growth increments are calculated, and where the adjustments discussed in this video are applied. There are no values on these sheets that can be edited directly, but they provide direct access to the daily numbers used to generate the data and charts displayed on the corresponding strategy sheets. In the case of Strategy 4, the Growth Model 4 sheets include size distribution charts for both harvests separately, as well as the combined chart that is displayed on the Strategy 4 sheet. Okay, so we start with mortality rates. The modelling of mortality rates is perhaps the most problematic element of the biological model, as they are either unpredictable or tend to increase under certain environmental conditions, which may be site-specific or seasonal. Furthermore, in this spreadsheet model, mortalities include losses from any cause, including predation, escapes or theft. In practice, mortality rates and other losses can be difficult to monitor, especially for reasons other than disease. The model assumes relatively low mortality rates and that these mainly occur after the first stocking, or the handling of fish when taking an interim harvest, or near the end of a production cycle when stock densities are at their highest. Each of the scenario sheets includes a chart showing assumed cumulative mortalities expressed as a percentage of stock, the line, and also as biomass lost, the vertical bars. The mortality formula is simply an exponential function, with the input values being the number of mortalities on a specified day, e.g. the day of stocking, or the day of partial harvest, or day of final harvest, and a parameter that determines the daily rate of decay from that number. The number of mortalities on the first day is calculated based on your estimate of the percentage of stocked fish that die within the first 24 hours after stocking, i.e. mortalities on day T equal mortalities on the first day times the exponential of L times T, where L is the rate at which the daily number of mortalities decline, and T is the number of days after stocking. As the spreadsheet calculates the stock numbers daily, this can be simplified to mortalities on day T equals the mortalities on the previous day times the exponent of L. The L value is always negative, so mortalities decline after the initial losses. Values of between minus 0.05 and minus 0.25 are suggested. You may already have data on the percentage of fish that die on the first day after transfer, but you may need to experiment with the L value to find something that matches your records. We can see here the impact of changing the L value from minus 0.05 to minus 0.5, assuming first day mortality of 0.6% of the stocked fish. It can be seen that the more negative values steepen the mortality curve, so the daily rate reduces at a greater rate, resulting in far fewer mortalities overall. The suggested initial values for first day mortalities and L are 0.6% and minus 0.15 respectively. The same equation, although with different parameter values, is used to model mortalities after partial harvest of a cage where the remaining fish have been stressed. To model an increase in mortality in the late stage of the production cycle, a slightly modified equation can be used. This effectively reverses the curve so that mortalities increase to a fixed final value. Again, the slope of that curve is determined by the L value, which remains negative. Taking an example where 0.1% of the stock dies on the final culture day, we can see the difference between an L value of minus 0.05 and minus 0.5. In this example, the less negative number means a shallow slope, so overall there are substantially higher mortalities than in the second example, where the increase in mortalities happens faster but much later. The suggested initial values for final day mortalities and L is 0.1% and minus 0.2 respectively. It can also be seen from these charts that mortalities at the end of the cycle have a much greater impact in terms of biomass and hence result in much greater financial loss. Fine-tuning the mortality models is therefore very important for improving the accuracy of financial projections. Next, we look at the density factor. The growth of tilapia can be affected by the density of the fish in a cage, usually measured as kilograms of fish per cubic metre of water. When the density is very high, there can be a deterioration in water quality, especially if there is fouling on the nets. This results in a reduction in feed intake and growth. It has been noted that growth can be lower at low densities. This may be due to the fish being more stressed, or it being more likely that feed is lost from the cage before it is eaten by the fish. Based on your experience, you can compensate for these effects in the model using the density factor table. Click on the density factor button on the 0-Start Here sheet to go to the table. You can enter different fish densities in the left column in kilograms per cubic metre, but they must be in ascending order. Enter a corresponding adjustment factor as a percent of full growth performance in the right column. In this example, it is assumed that fish grow at their full potential until the stock density exceeds 35 kilograms per cubic metre. It then declines as stock density increases. The density multiplier is applied to the calculated SGR in the growth models. This means that at high densities the feed amount is not reduced, but the growth achieved is lower. This results in higher FCR values, i.e. wasted feed. One important caveat to keep in mind is that density of 35 kilograms per cubic metre of small fish, for instance, is not the same as 35 kilograms per cubic metre of large fish, since the smaller fish have a higher metabolic rate and therefore will require more oxygen. Finally, in this video, we consider size variability. Within any population of fish, there will be a natural size variation between individuals. This will depend partly on genetic diversity, but also on management practices, such as grading and control of feeding. For modelling, it is assumed that sizes are normally distributed around the mean value, i.e. more fish close to the mean weight and fewer that are significantly larger or smaller, but an equal number of smaller and larger fish. If this is not the case, then the model may give misleading results. In particular, note that the size distribution is calculated in 100-gram bands, so if the fish are grown to, say, 200 grams or less, there will be insufficient resolution in the charts to show a normal distribution. The spread of sizes can be controlled by adjusting the coefficient of variation, CV, in the advanced setup section. CV is calculated as standard deviation divided by the mean and is usually expressed as a percentage. You can find this number for your typical harvests by individually weighing a large sample of fish and recording the weights in a column in Excel. You can then use the built-in Excel formulas to find the mean of the numbers and the standard deviation. Normal values for CV are generally between 22 and 26%. The higher the value, the greater will be the spread of sizes around the mean. So, with this video, we have completed a run through the biological and production parameters that can be adjusted. In the next video, we look in more detail at entering financial data.